all, let's do just a teeny tiny bit of review because we've had a 4-day weekend, right? So first of all, what do we have to do in stoichiometry? The first thing we had to do in our homework problems was we had to what? We had to write and balance an equation, correct? Wow, my handwriting is really bad on this one. Okay, after we had our balanced equation, then we had to write down what we are starting with, what we were given, however you want to say it, right? Then, if it wasn't already in length, we had to convert to moles. If we were not already in moles, we had to convert to moles. So now we are in moles. Then what did we have to do? We had to use our mole ratio to do what? What was the whole point in doing the mole ratio? So we could switch what part of the unit? The compound, right? Yeah, I ran out of room, but you guys, that's compound. Okay, after we have used our mole ratio to change our compound, then what did we have to do? Not necessarily molar mass, but we had to convert to whatever we wanted. So this could have been grams, it could have been atoms, it could have been molecules, it could have been etc., right? Liters, whatever. Okay, now that we are in our desired unit, the very, very, very last thing we did, we waited until the end. What did we do? We calculated it and checked our significant figures, correct? That's just a little refresher course. That's what we did before our 4-day weekend, correct? Now, what I like to stress about today is this is not changing. All we're learning today, honestly, is some more vocab terms. We're going to learn 5 new vocab terms, and we're honestly just going to relate it to stoichiometry. We're doing the exact same thing. I'm not changing the process at all. We're doing the exact same steps. Nothing's changing. We're just learning different context words, okay? Is everybody done with these? Ish, maybe, kind of, sort of. Yeah? Okay. So the first vocab term I want to talk about is something called the limiting reagent. Now, you can say reagent, you can say reactant, you can say, honestly, those are the only 2 I say. Limiting factor, sometimes you hear it as a factor, but the key word here is limiting. If you are given 1 dozen loaves of bread and a gallon of mustard, but only 3 pieces of salami, you can't make very many sandwiches, can you? You can honestly only make 3 sandwiches, correct? So in this scenario, our salami is limiting how much product we can make, correct? I know this sounds like a silly example, but you guys can visualize a salami sandwich in your head, or a sandwich of any sort. You cannot visualize aluminum plus bromine, correct? So, in this scenario, we can only make 3 sandwiches because we only have 3 pieces of salami. So in this scenario, our salami is limiting our product, correct? So that means our salami, I cannot say that. Our salami is our limiting reactant, which means we are going to run out of it first. Once we run out of salami, can we make any more sandwiches? No. Well, we could make bread and mustard sandwiches, but that's not very good. Okay? This makes our bread and our mustard, which we're going to have plenty left over, our excess reactant. In other words, these are our leftovers. We're going to have some, when the reaction is done, we're still going to have some bread. We're still going to have some mustard. The limiting reactant is the one that determines how much product you can make. I need you to star this, and I need you to underline it. When we are doing stoichiometry, you need to start with your limiting reactant. Okay? Now, if you notice, when I was talking about our salami sandwich, we have 3 pieces of salami, which means we can make 3 sandwiches, correct? If I have a dozen loaves of bread, let's say that gives us 60 slices of bread. Way more than that, probably. But if we have 60 slices of bread, we could theoretically make 30 sandwiches, correct? But if you think about it, I'm talking in terms of how many sandwiches. I'm talking about the product. So when you're thinking about our limiting and our excess reactants, you need to think about how much product they can make, not how much reactant you have. That makes sense to everybody? You have to think about what's on the other side of the arrow. So, in a chemical reaction, an insufficient quantity, or in other words, if you don't have enough of any of your reactants, this will limit the amount of product you can form. So I can continue to add bread and mustard, but it's not going to change the number of sandwiches I can make. I can still only make 3. The only way I can change the amount of sandwiches I can make is if I increase my salami. Go to the grocery store. All right, so let's go back up to that list that we just made. Maybe. This list that we just made, hopefully it'll pop up. Okay, let's add to it. Write down what you were given. This is our limiting reactant. So when you are doing stoichiometry, when you're trying to figure out how much product you need to start with your limiting reactant. So up on that list we just made, we are adding to step number 2 that when you write down what you're given, you're writing down your limiting reactant. That's the one that's going to affect how much product you can make. All right, so now the question is, well, how in the world do you determine which one's limited? Because we can visualize salami sandwiches, but we cannot visualize aluminum plus bromine. We can't figure out how much product. That's not that easy. So there has to be another way to do it. Well, first of all, when you're given this type of problem, the way you can know that this is a limiting reactant problem versus a normal stoichiometry problem, because you're given 2 amounts of chemicals. These problems you will be given 2 numbers. As of now, when I give you guys stoichiometry problems to do, you're given 1 number. That's the one you start with every single time, right? Well, starting today, you're going to be given possibly 2 numbers. If I give you 2 numbers, you have to figure out who the limiting reactant is in order to know how to do stoichiometry, right? So step number 2, we now just edited to say that we had to do it with the limiting reactant. Now, to do this, technically you're supposed to do 2 stoichiometry problems. You have to do 1 for the first reactant, figure out how much product you have. Do 1 for the second reactant, figure out how much product you have. But since we had 2 snow days, I'm not going to make you actually do this step mathematically. I expect you to be able to understand how we did it, and I expect you to be able to understand that the limiting reactant is who we do the stoichiometry problems with, but I'm never going to actually make you do the next slide in real life. Does that make sense to everybody? I'm going to walk you through it. I expect you to know the process, but again, I'm not going to make you do it all by yourself. Okay? So, in other words, I'm going to walk you through this next one. I do not expect you guys to be writing it down, because like I said, we don't have to do this one. All right, so let me walk you through one. Now you do not need to be writing this down. This is not going to be on the test. It might be the extra credit question, but it's not going to be how do you do this. So basically, if 10.6 grams of copper reacts with 3.83 grams of sulfur, how many grams of the product will be formed? Well, right off the bat, we have two amounts there, right? 10.6 and 3.83. So that's signaling to me automatically that I have to determine the limiting reactant. I have to figure out who is going to give me more copper sulfide. Okay, and it's not as easy as looking at which mass is bigger. That's not how we do it. You actually have to physically go through the process. So what you do is you start with the first reactant. Let's start with copper. We have 10.3 grams of copper. Well, what's step number 2 in stoichiometry? We write down what we started with, right? Did we write it down? Then what do? We convert to moles. We have to use the molar mass, right? After we convert to moles, we do what? We use our mole ratio. Where do we get those numbers from? The equation, they're the coefficients, right? Now that we have changed our compound, we need to do step 5, which was convert to whatever we want. We want grams. And then step 6, do all the math and get our answer with significant figures, right? And we get an answer of 13.3 grams. So if we start with 10.6 grams of copper, we're going to get 13.3 grams of copper sulfide. Okay? Well, remember, we're trying to figure out who our limiting and who our excess reactant is. We've solved one piece of the puzzle, but we don't have anything to compare it to, right? So we need to do the other part of the puzzle. So we start with our other reactant. We're going to start with 3.83 grams of sulfur. What's the next step in stoichiometry? Convert to moles. Then what do? Mole ratio. Where do those numbers come from? The equation. Now that we've changed our compound, we need to do what? Convert to what you want. So this time we want mass, so we're going to use our what? Molar mass. Now we're in the correct unit, so we get to do the math, significant figures, right? And we get an answer of 19 grams of copper sulfide. So if we start with 3.83 grams of sulfur, we're going to get 19 grams of product. If we start with 10.6 grams of copper, we're only going to get 13 grams of product. What does that tell you? Our copper is our limiting reactant. In this equation, our copper is our salami, right? That is determining the number of sandwiches we make. We can only make 13 sandwiches versus the 19 sandwiches. So in this reaction, our copper is our limiting. Everybody wants to look at the amount. They want to go, we have more copper than we have sulfur. That doesn't matter. Okay, because remember, we have a whole bunch of conversions in here. We have molar masses to consider. We have mole ratios to consider, right? So you can't look at the amount you start with. You have to look at how much product you can form. So since 13.3 is smaller than 19, copper is our limiting reagent. Now, again, do I expect you to be able to do this process? No. Do I expect you to know what to do if I tell you something is a limiting reactant? Yes. All right. So those were our first two vocab terms that I wanted to talk about today. The next one is something called yield. In chemistry, what does the word yield mean? To produce. So we're talking about products, right? All right, well, in chemistry, there's actually 3 types of yield. And again, yield in chemistry means products. We're producing something. So we have something called actual yield. This is what we got in lab. If I go into the lab and I take my aluminum and my copper and the equation I was just dealing with, if I take that in the lab and I actually do the reaction, my actual yield is what I physically measure in the lab. So if I go back there, and we were trying to determine copper, right, in the last equation. If I go in the lab and I actually get 12 grams of copper, that's my actual yield. It's what I went in the lab when I did the equation, when I did the work, that's what I got. My theoretical yield is what I should have gotten. What I should have gotten is what you do using your balanced chemical equation using stoichiometry. So mathematically, this is the answer I should have gotten. Do you think these answers are ever going to be the same? No. Why do you think our theoretical yield and our actual yield are not going to be the same? What do you can't control the experiment. First of all, we're human. So we're going to have mistakes, correct? Maybe we didn't read the thermometer correctly. Maybe we accidentally spilt some of our reactant. Maybe our scale wasn't calibrated. Okay, and those are just talking about the human errors. There's always things in reactions that we physically cannot control. Some reactions don't happen. Some reactions happen all by themselves. Okay, so, and then this leads us to something called percent yield. Percent yield is just like a percentage. When you try to find the percentage you got on a test, you take what you got divided by what you should have gotten. So in this one, you take what you actually got, you divide it by what you theoretically should have gotten. So going back to our salami sandwich, we had 3 pieces of salami. Your mom goes in the kitchen. She's going to make salami sandwiches for lunch. There's 3 of you, so yay, everybody gets a sandwich. Well, she accidentally drops it on the floor. Your dog runs in and eats it. So theoretically, she had enough materials to make 3 sandwiches, but how many did she actually end up making? 2. So her percent yield is only going to be 67%. So she gets a D for the day. Yikes, right? All right, so let's walk through an example. Okay, this problem, and this is exactly like what your homework problem is going to be tonight. It says 6.78 grams of copper is produced when 3.92 grams of aluminum are reacted with excess copper sulfate. Excess copper sulfate. What's that mean? Excess copper sulfate. It's telling you that copper sulfate is left over, so that is in our excess. Well, if that reactant is in the excess, then the other one must be the limiting. So like I said, I'm not going to make you guys do the math to determine who's limiting and who's excess. I will tell you which is which, but you do need to be able to know which number you need to use. Okay. So the first question, what is the actual yield? Well, it says that you got 6.78 grams of copper is produced from 3.92. So what they actually got in the lab was 6.78 grams. That's what they actually got. But we're actually going to try to determine percent yield. Okay, so next, in order to find percent yield, we need to first find the theoretical yield. How do you think we should find the theoretical yield? Well, what should we have gotten? They got 6.78, but how can we figure out what they should have got? We need to do stoichiometry with the limiting reagent, right? So we already have our balance equation. What's the next step? Write down what you start with. So we are going to start with 6.78 grams of aluminum. Oh, wow. I can't write. .92. I can read. 3.92 grams of aluminum. There we go. That's better, right? Now that we've written down our limiting reactant, what do we do next? Convert to moles. So I need a reaction that allows me to go from moles to grams, which is called molar mass, right? Where do I get my mass amount? From the periodic tables. If we look up here, my aluminum is 26.98. This unit cancels out this unit. We're left with moles of aluminum, which is not exactly what we want. So the next step in stoichiometry is to what? Use your mole ratio. We're going to put what we want over what we have. We want to go to moles of copper. We have moles of aluminum. Where do I get these numbers from? The equation. The coefficient in front of copper is 3. The coefficient in front of aluminum is 2. This unit cancels out this unit. We're left with moles of copper, which is not quite what we want. So what's the next step? Convert to what we want, which is grams, so we need molar mass. So 1 mole of copper, we look at the periodic table, has a mass of 63.55. That unit cancels out that unit, and we are finally ready to do our math. So I'm going to do 3.92 divided by 26.98 times by 3 divided by 2 times by 63.55, and I get an answer of 13.9. Wow, that was a bad 3. Okay, do my significant figures match? Yes. So finish it off with unit grams of copper. So I figured out my theoretical yield. My actual yield is 6.78. So I should have gotten 13.9, and I only got 6.78. Yikes. If I had to guesstimate, I'm going to guesstimate that's about 50%, right? But do you think we should guesstimate? No, we're actually going to do the math. Is it okay if I erase this?
Sure.
Okay, somebody remember 13.9 for me. Guess I forget.
2.9.
Okay, to find our percent yield, we need to take what we got and divide it by what we should have gotten. So what they actually got when they did this experiment was 6.78 grams. We just calculated that we should have gotten what? 13.9 grams. Okay, whenever you do percentages, remember you have to times it by 100. So if I do 6.78 divided by 13.9, I get an answer of 48.8%. So we were pretty close, weren't we, when we guessed 50%? This person was only 48% accurate. That's not very good, right? That'd be like getting 48% on your test. That means that either this reaction doesn't happen very well, or they made a lot of error when they were in the lab. All right, so what does all of this tell us? Yeah, we just rounded a little bit differently. Okay, percent yield tells us how efficient our reaction is. Now, efficiency can be the reaction itself or us humans doing the reaction. But the important part is percent yield cannot be bigger than 100%. I can guarantee that either you as a human or the reaction as in general is not going to be perfect. One of the two will happen, and you will not get 100%. Okay, 100% honestly is pretty impossible to be because we're not perfect. Reactions aren't perfect. Okay, theoretical yield will always be larger. Why will always be larger? Again, because we are not perfect and the reaction itself is not perfect. There are always circumstances out of our control that we will not be able to do perfectly in order for the reaction to happen perfectly. All right, you guys ready for another example? Okay, thanks to the snow days, we don't have to do problems like 12.7 or problems like 12.8. But let's look at 12.9 because we will have to do ones like this. 12.9 says, calcium carbonate, which is found in seashells, is decomposed by heating. The balance equation for this reaction is calcium carbonate will yield calcium oxide plus carbon dioxide. What is the theoretical yield of calcium oxide at 24.8 grams of calcium carbonate is heated? I don't know about you guys, but I don't like word problems. Do you?
No.
That's very wordy, correct? So first off, I just like to kind of isolate it. We're going to have 24.8 grams of calcium carbonate, and it wants to know how many grams of calcium oxide are going to be produced. That's what the problem's asking us. Do we have to worry about limiting an excess reactants in this problem? No. Why? Why don't we have to worry about limiting an excess reactants? Because we only have one reactant. If we only have one reactant, there is no limiting, there is no excess. All right. So we need to know, we're going to try to figure out how much we should get in this reaction. If calcium carbonate decomposes like it should in a perfect world, how much should we get? All right, so we need to do some stoichiometry, right? And if you keep note, it's a 1 to 1 to 1 mole ratio, so all our coefficients are 1. So let's get that. All right, so I'm starting with my 24.8 grams of calcium carbonate. What's my next step? Convert to moles. So I need a mole ratio. So 1 mole of calcium carbonate is how many grams? Well, this one's going to be a little bit harder to do in our head, isn't it? Because there's so many atoms. So calcium is 40.08. Carbon is 12.01. And oxygen is 16, but we have 3 of them. So if you do all of this, you're going to get an answer of 100.09 grams. So 1 mole of calcium carbonate is going to equal 100.09 grams. Now, where did I get all of these numbers? Periodic table. Okay, so now that we're in moles of calcium carbonate, what's my next step? Mole ratio. I'm going to put what I want over what I have. I want moles of calcium oxide. I have moles of calcium carbonate. Where am I going to come up with these numbers right here? The equation, which luckily for us is a 1 to 1 to 1 ratio. So all of our coefficients are 1, so that makes some easy math for us, doesn't it? Okay, those cancels that. That unit cancels out that unit. We're left with moles of calcium oxide. We're getting there. We're almost there, right? But we don't want moles. We need grams. So I need another conversion factor. Sorry, I ran out of room. I need a conversion factor that allows me to go from moles to grams. Where can I get this information from? The molar mass periodic table. Calcium is 40.08. Oxygen is 16. So 40.08 plus 16 gives us 56.08. Right. This unit cancels out this unit. We're left with grams of calcium oxide. So finally, we're ready to do the math, right? So if I do 24.8 divided by 100.09 times by 1 divided by 1 and times it by 56.08, I get an answer of 13.9 grams calcium oxide. Now what is this? We learned some new vocab terms today, right? What is this amount? This is my theoretical yield. This is what I should get. If I do this reaction in a perfect world, I should get 13.9 grams of calcium oxide. Okay? Well, is it a perfect world? No. So, now let's figure out. They actually did this experiment, and they didn't get 13.9 grams like we just figured out. They got 13.1 grams, right? It is not possible to get over 100%. So we just figured out that they should have gotten 13.9, but they didn't get 13.9. They got 13.1, which is exactly how I feel. And on tests, I feel like you should get 100% because I give you all the test questions the day before, and I give you all the answers if you come to the review session, right? So you should get 100%, but you don't, and that's okay. So how in the world do I figure out your percentage? You take what you got and you divide it by what you should have gotten, right? Well, they got 13.1. They should have gotten 13.9. In percentage land, we have to times by 100, correct? So if you do 13.1 and divide it by 13.9, we get 92.24446. So round that with significant figures, and we get 92.24446. 2. 94. I can't do that. 94.2%. So is this reaction a little bit more accurate than the last one we did?
Yeah.
Yes, so they are going to get approximately 94% of their limiting reactant is going to produce the product like it's supposed to. 6% is not going to do what it's supposed to. All right. So we really only learned a couple new vocab terms. I didn't change the math on you, did I? I added percentages a little bit, but I didn't change the math on you. So I want you guys to give this one a stab. Not this one. This one. I want you guys to give this one a stab. It looks like I went away. Make it come back.
This one.
It went away. Maybe. All right, I want you guys to give this one a stab. It looks, there's 4 questions, but it's only one problem. I broke up the questions into different ones so that it would help you guys go through the steps. So, answer these questions. You have 5-6 minutes in class to do it. If you don't get done, I post it on the website, but you should honestly be able to get done in the next 6 minutes, okay?